kinetics, non-isothermal kinetics. Where you heat or cool at a particular rate phi, so your d alpha dt equal to d alpha, because alpha is changing with temperature, that's what you can measure, and your dt how, that is the rate of change of temperature. Then, and you know the basic equations, the other basic equations is d alpha dt, rate equal to k f alpha, and k is your a exponential minus e over rt, and g alpha equal to kt, and g alpha is also integral 0 to alpha d alpha and d alpha over f alpha. Isn't it? Is d alpha expression I have written correctly? And we have our temperature integral or exponential integral, which is given by, so that py, what is py? Integral of y to infinity,
e to the power minus y by y
e
square
to the power minus y over y square dy. This integral approximate, Lorentz approximation is
minus 2.133.
approximation says log of py, natural log, log py equal to
minus
minus
2.315
minus 2.315
minus
minus 0.4567
y
y. So this is linearly varies within a range of
20.
around 30 to 50. So what is the range usually found for E over RT? What is y? Y is nothing but E over RT. So this Py actually is the R over E. It is not so this is actually R over E 0 to t exponential minus E over RT dt. That's the integral we come across, because ultimately, because we have this type of equation g alpha equal to ae over phi r py. So we have seen in the last class g alpha equal to a p over phi r multiplied by py. So you need to have this integral, and integral is direct solution is not available, so we use approximate solution. So we used these, or we use Coates-Redfern approximation, Coates and Redfern approximation, which says what?
py is what?
Py equal to
e to the power minus y by y square
e to the power
minus y by y square
minus y over y square multiplied by
1 minus 2 by y.
1 minus 2 by 2. Very good. So we discussed model free methods. Can you switch on the lights, please? We first discussed model fitting type of methods. Two methods I think I discussed. One is the direct differential method, another was Coates-Redfern method. The third, then 4 models we were going to discuss was model free method. You do not need to know prior expression of in prior hand expression of either F alpha or G alpha. The first method that we discussed under that model 3 method was Kissinger method, usually used for DTA, DSC type of thermal analysis experiment, where you heat or cool at a particular rate and you find out the peak temperature. Peak temperature usually corresponds to the maximum rate of reaction, and we have found out a particular condition for maximum rate of reaction. So at that peak temperature, we found out that ln phi over P maximum, that maximum rate, the peak temperature, Tp squared, that varies with 1 over Tp linearly, and from that the slope will be minus E over R. You can get the activation energy. So for that you need to do different heating rate experiment. Different kinetic curve you will get, and you can find out for each value of phi, what is the Tp. Then you plot ln phi over Tp squared versus 1 over Tp. From the slope you can get the activation energy. But this activation energy will be an overall activation energy. Here you are not getting activation energy as a function of alpha. The next 3 methods I am going to discuss, where you can get activation energy as a function of alpha, and also those are model 3 method. The first one of those the first one is Ozawa clean wall model.
So Kissinger is also model 3.
Yes, ultimately although they started with a rate law, but ultimately when you are using experimentally, you are just doing different heating rate experiment, finding out the peak temperature and plotting ln phi over Tp square versus 1 over Tp. That straight line, slope of that straight line will be will give you the activation energy, will be minus E over R. If it is not a straight line, use some other rate law, other function. Okay. So the next one we are going to discuss is Ozawa, OZAWA, clean wall. So in short, this is called OFW model. Ozawa and clean wall, they independently derive this model. It is same, like they started with G alpha equal to AE over phi R multiplied by Ty. What we derived in the last class, that expression out there, and then take common logarithmic of both sides. So log of G alpha, log of AE over phi R plus log of Ty, and log of Ty, they use this Duell's approximation. Duell's approximation, they use log of Ty. So in place of log of Ty, please pay attention, do not ask me again, because minus 2.315. So they used Duell's approximation for the log of Ty, and this is the expression. And then replace just y by E over RT, E over RT, y equal to E over RT. So that is the expression, and you rearrange this thing. You take phi this side and G alpha this side. So the G alpha you take here and phi you take here. So you will have log of phi equal to log of common logarithmic of AE over R multiplied by G alpha minus 2.315 minus 0.4567 y Q over RT. Now notice that if you do an experiment where you fix the alpha value for till a particular fraction transform for a particular heating rate, so fix the alpha value, say alpha value is fixed, say particular alpha value. For a particular alpha value, G alpha expression is fixed, it's a constant. So this thing is constant. So this, if you plot different, if you do different heating experiment, say you are doing different heating rate experiment and you are measuring alpha and alpha versus T you are measuring. These are different heating rates. Say phi 1, phi 2, for different heating rates you are getting this. So for a fixed value of alpha, for a fixed value of alpha, say alpha 1, fixed value of alpha, you find out for that heating rate, for that alpha, what is the temperature, corresponding temperature. So these are your T1, T2, T3, T4. So now you have T value or different phi values. So you can have 1 over T. So for different phi values you can have different 1 over T value. So for a fixed alpha. So for that alpha, if you plot log phi versus log 1 over T, from that slope you will be able to get E corresponding to that alpha. So you will get E corresponding to alpha 1. So you repeat this for different alpha. So you will get E corresponding to different alpha values. So you are getting, so from the plot of log of phi versus say 1 over temperature, from that slope you are getting E for a fixed alpha 1 or alpha 2 1, and after that these E values can be plotted against alpha values. So for different alpha you can get corresponding activation energy. So activation energy can be found out as the progression of the reaction. So this plot, when you plot activation energy versus alpha, this plot is called isoconversion plot, because this method is called isoconversion method. This method of finding out activation energy, isoconversion, meaning that for a fixed conversion value alpha 1 you are finding E value. Similar, so for different fixed alpha values you are finding E value. So this is a isoconversion method. And also you do not need to know the exact expression of G alpha. For a fixed alpha this is constant. So if you plot this versus this, you will get, you do not need to know the expression for G alpha. The next one is called Coates-Redfern method. Not Coates-Redfern. Coates-Redfern was model fitting type, huh? So the next one was Barnham and Braun, which is actually the modified Coates-Redfern. Why I am saying that? Barnham and Braun, they have transformed the model fitting Coates-Redfern method to an isoconversional method. Because the Coates-Redfern methods, what did they do? They started with the integral form G alpha equal to AE over phi r Py. They started with that and then they took Py approximation of Coates-Redfern. So AE over phi r e to the power minus y over y square 1 minus 2 over y, 1 minus 2 over y, and from there they put E over RT to find out that G alpha over T square equal to ln of G alpha over T square is ln of AR over phi E 1 minus 2 RT over E minus E over RT. So this is, till this line, it is same as what Coates-Redfern did. Coates-Redfern did. Same as that. What Barnham and Braun did, they just modified, they just simple modification of this, meaning just take this phi this side and G alpha this side. That's all they did. So if you do that, then the expression will look like ln phi over T square, and here you write G alpha. So again, like this method, for different phi value, you plot the kinetic curves. Then for a fixed alpha value,